All right. In this section, again, we're constructing confidence intervals, but not of sample means or population means. Now it's going to be proportions. Now, in some ways, this is going to be similar to working with means in that, you're going to be working with calculating margin of error, and we're calling this error bound of the proportion instead of error bound for the mean. But what's going to feel similar, to what you did before is you're just going to use a normal distribution when you're calculating the error. We'll get into what P prime and Q prime means here in a minute. And then you're also going to be calculating sample size, and there's two different equations for sample size, but it's based on whether you know the sample proportion or not. All right, so um, that's really all there's going to be to it in terms of proportions, really. Um, so let's kind of start into that here. So let me give you some context. So one sees population proportion confidence intervals in politics where a candidate has 40% of the vote, plus and minus 3%. Often election polls are calculated with 95% confidence levels. Therefore, pollsters would be 95% confident of which political candidate the true population proportion of voters favored. What's the definition of the proportion of a sample? So we're going to use P prime to denote the proportion of a sample and just P, lowercase p, for the proportion of a population. Now remember, to kind of help you with what we talk about when we're talking about a proportion, is remember when we calculated probability of an event, right? Probability of an event was the order of the event over the order of the sample space. And so, for example, if our sample space was all of the elementary outcomes of a six-sided die, and our event was an even result, then you would consider a 2, 4, or 6 on one six-sided die to be a success. So in a similar way, one considers a sample proportion to be equal to this fraction of the number of successes over n, which is the sample size or the total number of trials. The sample proportion, so the sample proportion P prime serves as a point estimate for the population proportion. And so P prime represents the sample proportion of successes, and Q prime represents the sample proportion of failures. And Q prime can be calculated by taking 1 and subtracting P prime from it. And likewise, the sample proportion Q prime also serves as a point estimate for the population proportion Q. P prime, so both P prime and Q prime are point estimates for an unknown population proportions of P and Q. P being the proportion of successes, Q being the proportion of failures. So if we let capital X represent the random variable for the number of sample successes, and capital P prime be the random variable for the sample proportion, then P prime follows a normal distribution for proportions. So the distribution of proportion of successes is normally distributed with a So I want to say mean, okay, but with a proportion P, and this is the population proportion, and a standard deviation of the square root of the population proportion of successes times the population proportion of failures divided by n, and the square root of all that. So hence, we're going to use the picture of a normal distribution in conjunction with our inverse distribution function, inverse norm, to calculate z-scores for calculating margin of error to get the desired confidence interval. Okay, so I think that is the end of that explanation. Let me know if you have any questions.